Namaskaram. Today we will see one application of absolute extrema on a multivariable function. The solution of last homework. Okay, this result is useful. If a function f of xy has an absolute extremum means either absolute maximum or absolute minimum, at an interior point of its domain, then this extremum occurs at a critical point. This means what? Suppose this is our domain and we have a function fxy, and this result says that if if the absolute extremum exists, maybe it is maximum or minimum. Okay, if it is exist, then it is an interior point. That point is inside this domain. That's the idea. There is no restriction for this domain. Domain may be unbounded, maybe open, whatever be. Okay. Okay, consider this problem. Determine the dimensions of a rectangular box open at the top having a volume of 32 feet cube and requiring the least amount of material for its construction. Okay, so here it is given that the top is open, and we have to find the least amount of materials for constructing a rectangular box having volume of 32 feet cube. Okay, that's our problem. Okay, so there is no top portion. We have 1, 2, 3, 4, 5 sides. Okay, so here we assume that x is nothing, it is the length of this box, and y is the width, and z is height of the box. Okay, and we have to minimize the material. That means we have to minimize the surface area, lateral surface area. Okay, so we denote that surface area denoted by s, including 1, 2, 3, 4, 5 sides. Okay, excluding the top portion. Okay, so what is our problem? We have to minimize the lateral surface. So let it be S. So what is our S in terms of X, Y and Z? We have only one bottom portion, that is area is XY. And what about area of this portion? That is YZ. And what is the area of this portion? That is XZ. But there are two such surfaces. So plus 2 times XZ plus 2 times, there are two such surfaces. One is this one, other is this one. So that is 2 YZ. So this is the total lateral surface. Total, no, not lateral. This is the total surface area we have to minimize. Okay. And subject to what? Subject to there is a condition. What is the condition? The volume is given. Volume is 32 feet cube. What is the volume of this box in terms of x, y, z? Yes, x, y, z equal to 32. So we have to minimize this quantity subject to this condition. So that is our mathematical version of this problem. Minimize s is equal to xy plus 2xz plus 2yz subject to our volume equal to 32. Okay, now our function s involves three variables x, y and z. But we have an extra condition, a restriction is there, x, y, z equal to 32. So I'm going to convert everything in terms of two variables x and y using this relation. From this relation, what is our z value? Z is equal to 32 by xy. Next, I'm going to replace all the z values in this expression by this 32 by xy. So what about s? What about new s? Yes, our s become xy. There is no change in xy plus what is the second term? Second term is 2xz. So just replace z by this quantity. So the second term become 2x times z become 32 by xy. Okay. Similarly plus 2y into z. What is it? 32 by xy. Okay. You can cancel this x. Here you can cancel this y. So our expression become xy plus 64 by y plus 64 by x. So we have to minimize this new expression. Okay. So our problem is reduces to like this. Minimize s is equal to xy plus 64 by y plus 64 by x in this region. Why? Because we know what is our x and what is our y. X and y's are the length and breadth of rectangular box, and we know that length is always positive. Okay, that's why we have one more assumption, a natural assumption, x is greater than 0 and y is greater than 0. So we have to minimize this function over this region. This region means this first quadrant portion except these two axes. Okay, because x is positive and y is positive. So the portion of the first quadrant except these two axes. Okay. Okay, but the problem is this region is unbounded and not closed. And we know by extreme values theorem, if a region is closed and bounded, then there exists a maximum and minimum. There exists absolute maximum and absolute minimum. That is only for, there is only theoretical guarantee for closed and bounded region. That is our extreme value theorem. Yes, this is our theorem, extreme value theorem. If f of xy is continuous on closed and bounded set, then f has both absolute maximum and absolute minimum on R. This is only for closed and bounded set. In our region, neither closed nor open. So there is no mathematical guarantee such that our function S has minimum, absolute minimum in this set. Okay, so there is no mathematical guarantee the existence of absolute minimum for this function S on this open unbounded region. Okay, but we have seen this result, and what is this result says? This result says that if a function f of xy has an absolute extremum at an interior point of its domain, then this extremum occurs at a critical point. Okay, what about our region? Our region is x is greater than 0 and y is greater than 0. This is our region. Okay, in this domain it is clear that it has no boundary points. Okay, it has no boundary points. So all the points are interior points for this function. Okay, so extremum exists. If extremum exists, then that extremum occurs only at critical point. That's the result. That means this is only an assumption. What is assumption? If function has absolute extremum, then at the critical point. That means suppose our function S has a minimum, absolute minimum on this region, then that is at a critical point. Okay, so next we are going to search the critical points of this function on this region. Okay, that is if S has an absolute minimum in this region, this open and bounded region, then if it is exist, then it must occur at a critical point. Okay, we don't know minimum exist or not. If it is exist, then only at a critical point. So anyway, we are trying to find all the critical points. Okay. Then how to find the critical points? Either function is non-differentiable or both partial derivatives are 0. It is clear that this function is differentiable in this region. Okay, because x is positive and y is positive. So we have to find those points with the two partial derivatives are 0. So what are the critical points? Okay, so we are going to consider the derivatives. So what is the derivative of s with respect to x? That is y minus, this term becomes 0, and this is 64 by x square. And similarly sy means derivative of s with respect to y, that is equal to x minus, and this term is minus 64 by y square, and this becomes 0. Next we have to equate these two equal to 0 and solve. So what are the critical points? Okay, so I'm just equating this is equal to 0 and this also equal to 0. And from this equation number 1, y equal to 64 by x square. And we have to solve these two. So I'm going to substitute this y is equal to 64 by x square in second equation. So second equation become, okay, this become x minus 64 by y square, and y square is 64 square by x square whole square. So this become x minus 64 into, you take the cross reciprocal, so x raised to 4 by 64 square. And you can cancel 164, and 1x is common, you can take outside. So this become x into 1 minus x cube by 64. Okay, and what is the meaning? Either, this means either x equal to 0 or 1 minus x cube by 64 equal to 0. And what about x equal to 0? Is it possible? No, because we have to optimize, we have to minimize this function over this region. Here x is positive and y also positive. So x equal to 0 is not possible. So you can neglect this one, x equal to 0. So we have only one possibility, 1 minus x cube by 64 equal to 0. By solving this expression, you can find x. What is x? Okay, so this become 1 equal to x cube by 64. That means x cube equal to 64. So what are the possible solutions of x cube equal to 64? Yes, we know that this third degree equation has only one real root, that is 4. Okay, so x equal to 4 is the only possible solution of this critical points. That means this system sx equal to 0 and sy equal to 0 has only one possible root, that x equal to 4. So when x equal to 4, what is the corresponding y value? Now x equal to 4, then what is the corresponding y value? That is 64 by 4 square. Okay, yes, that is equal to 4. So this problem S, this function S has only one critical point, that is 4, 4 in the region x is greater than 0 and y greater than 0. In this region, this function has only one critical point, that is 4, 4. Okay, so the problem, this function S has only one critical point in this region, that is xy equal to 4, 4. And what is the value of S at 4, 4? That is 48. You can easily find this one just substituting x equal to 4 and y is equal to 4 in this expression. This will give 48. So at this critical point 4, 4, our function S has the value 48. Okay, next we are trying to establish this 48 is the minimum of this function over this region. Okay. Okay, actually now our problem is to minimize this function over an unbounded region. We are trying to reduce this unbounded region to a bounded region. Okay, because you can easily remove so many points. For example, you consider a point like this, 100 comma 2. Okay, or you take another point like that, 2 comma 100, whatever, we no problem. Then 2 is somewhere here, 100 maybe somewhere here. Anyway, you think about this point, 2 comma 100. That means x value equal to 2 and y value equal to 100. And what about this point? Is it possible this point is a minimum point? Because no. Why? Because it is clear that when x equal to 2 and y is equal to 100, the first term itself 200, right? Which is greater than, already we have a minimum value. Already we have a value s equal to 48, which is at 4, 4. Okay. So it is clear that when the point is 200, 2 comma 100, at this point our this term, first term is already 200. Then remaining we have two more terms. That means 200 plus a positive quantity plus one more positive quantity. So ultimately the S value is greater than 200. Clear? So it is clear that this point is not a minimum point. Similarly, you can remove, suppose you consider another point, 48, 1. What about this point? Is it a minimum point? Because no, because at this point, what is the value? S is equal to 48 into 1. So first time itself 48. Plus we have two more non-negative terms, 64 by 1. This time is 64 and second time is 64 by 40. Anyway, we have two non-negative terms with this value. Okay, so 48 plus something. So it is clear that this is greater than 48. So now we have already one point 4, 4. At that point our function has value 48. Okay, so using this idea we can easily remove so many points. What are the points? Okay, using this idea you can easily remove so many points. So suppose xy is greater than 48. Suppose our first term is greater than 48. Then it is clear that automatically the whole sum is greater than 48. Okay, so you can remove those points. So those points with this property. Those points means set of all x comma y such that xy is greater than 48. So there is the guarantee is that in this set there is no minimum point. Clear? Similarly, you can remove all such points. 64 by is greater than 48. If this term is greater than 48, there is no minimum at that region. Similarly, or 64 by x is greater than 48, then there is no minimum. That means if our point satisfies either this condition or this, then our S value is strictly greater than. Okay, so we are going to analyze the problem except these points. Except these points means what? Either this or this or this. What is the opposite of this one? Yes. What is the complement? What is the complement of this set? Yes. Xy is less than or equal to 48 and this is OR. So and 64 by y less than or equal to 48 and 64 by x is less than or equal to 48. So we are trying to establish, we are trying to search what is the minimum of our this function on this region, because outside this region our s value is automatically greater than 48 outside this region. So we are trying to search what is the minimum of this function on this region, and what is this region. Is it bounded or and closed? What about the boundedness and closeness of this region? Yes, this region is closed and bounded because xy is less than or equal to 48 means, okay, what is xy equal to 48? It's a part of this hyperbola, right? So xy is less than or equal to 48 means it's the lower part, this region, because 0, 0 satisfies this equation. So this side. And what is 64 by less than or equal to 48? That means y equal to 4 by 3, right? Y is equal, no, so not, no, this implies what? This implies y is greater than or equal to 64 by 48, that is 4 by 3. So this is y is greater than or equal to 4 by 3. So above this line, y is greater than or equal to 4 by 3. And this implies what? This implies x is greater than or equal to 64 by 48. That means again that is also 4 by 3. So x is greater than 4 by 3, this region. And so intersection of these three regions. One is xy is less than or equal to 48. So this region, and above this one, and right side of this one. So it is clear that this region, this new region R, this is our R. This new region R is closed and bounded. Okay. So then how to establish this? This is our 0.44. This is our 0.44. It is clear that 44 belongs to this set. Okay, you can easily verify that 44 belongs to this set because 44 satisfies all these conditions. Okay, so 44 is inside. So how to establish this 44 is the minimum of the function s on this closed and bounded set? Yes, that is the way the method is like this. Suppose s is greater than or equal to 48 on R. Suppose it is possible to prove s is greater than or equal to 48 on R. Then what is the idea? Then minimum of s on this region is 48. Then automatically the minimum of s on this entire region, x greater than 0, y greater than 0, also 48. Okay, so next we are going to establish the minimum of s on this closed and bounded region is 48. That is very easy because we have concrete algorithm to find the minimum of a function on a closed and bounded set. That is our extreme value theorem. Okay, so how to find the minimum of this function on this one? Okay, that means suppose s is greater than 48 on our region R. The region bounded by R means the region bounded by these three inequalities. Okay, suppose s is greater than or equal to 48 on this region R, then the minimum value of s is 48 on this entire region, because we know that outside this region s is automatically greater than 48. Okay, we already established that outside this region s is automatically greater than 48. So the minimum of R is same as minimum on this region. Okay. Okay, so we have to minimize this problem. We have to find the minimum of this problem over this region, that is equivalent to the minimum of the same function over this bounded, closed and bounded region. Okay, then we know that extreme value theorem. By extreme value theorem, we know that this S has absolute minimum on this region because this region is closed and bounded. And what is the algorithm for finding this absolute minimum? We have mainly 3 steps. Yes, these are the 3 steps for finding the absolute extremum. Find the critical points of f of xy that lies interior of R. In this case, we have only one interior point, that is 4, 4, interior to this almost triangular shaped region. Okay, this is our R. And find all the boundary points at which the absolute extremum can occur. if there is a possibility on extremum, there is a if suppose there is a possible extremum on boundary, then we have to identify those points. But in this case, what happened? In this case, there is a slight difference. Okay, then after that, we have to find the absolute minimum and absolute maximum from those points. In this case, okay, in this case, on the boundary, what happened? Suppose you consider xy equal to 48. Our first boundary is xy equal to 48. It is clear that on this boundary, on this xy equal to 48, our first term value is 48. So we have two more terms, two more non-negative terms. So ultimately our s is greater than 48 on the boundary. So there is no possible extremum. There is no possible absolute minimum because already we have 1.44. Already we have 1.44 which is interior to this region R, and at this point our s value equal to 48. On this boundary, it is clear that our s is greater than 40. So there is no scope of minimum on this boundary. And similarly, this boundary means what is the value? Okay, on this boundary, our y value equal to 4 by 3. Y value equal to 4 by 3. Y value equal to 4 by 3 means what? This means our 64 by y. This means our 64 by y is equal to 48, right? Y equal to 4 by 3 means our 64 by y is equal to 48. So already this term is 48 and we have two more plus terms. So again s is greater than 48. Similarly, on this region, on this boundary, our x value equal to 4 by 3. When x equal to 4 by 3, this term is 48. This term is 48. So we have, similar to previous two cases, we have two more positive terms. So again s is greater than 48. So it is clear that there is no scope for our step 2. There is no possible minimum points on these three boundaries. So on the boundary, our s value is automatically greater than 48. So what is our guarantee? So our guarantee is the minimum of s on R at the critical point 44, because the guarantee is either our we know that absolute minimum either interior or the boundary. There is no chance in the boundary, so absolute minimum only on the critical points. We have only one critical point which is 4. So the absolute minimum of this function at 4. Okay, so the absolute minimum of s on this region R at 4, and the value of s is equal to 48. And we know that, therefore, you can easily claim that the absolute minimum of s over this region, over this entire region, is also 48. Why? Outside this triangular shaped region, already we know that s value is greater than 48. Okay, so that's why we concentrate our attention on this particular closed and bounded region, and in this region the minimum at this 4. So minimum of this function over this region, this unbounded region, is also 48. Okay, so what are the values, or what are the minimum values of dimensions x equal to 4 and y equal to 4? If you substituting x and y in z, what is our z? Z is equal to 32 by xy. Okay, we know that x, y, z equal to 32. So z is equal to 2. So these are the minimum dimensions of that box, which minimizes the surface area. Okay, that means we need 48 square feet of materials to construct such a minimum. We need this much of material for construct such a box. Okay. Okay, this is your homework. Thank you.